So we just learned how to calculate the delta S of the reaction. So given any kind of reaction now, we can calculate delta S using those absolute molar entropy values. But the delta S that we calculate just now is actually the delta S of the system, which is the delta S of the reaction itself. Remember that in chemistry, the chemical reaction, which is the reactants and the products, are the components of the system. But what the second law of thermodynamics says is that to predict spontaneity, we need to know the value of delta S of the universe, because it's the positive value of the delta S of the universe that tells us that the process is spontaneous. So right now, we have calculated only the delta S of the system, which is just written as delta S. Usually that subscript system is not included. And what we need is the second component of it, which is the delta S of the surrounding. And it's the sum of those two numbers that has to be positive in order for the process to be spontaneous. We can see why just getting the delta S of the system is not enough. So for example, here's the reaction of the condensation of water. H2O gas goes to H2O liquid. And you can see even without looking up the molar entropy values, you can tell that that process is going to have a negative entropy change because you're going from a gas to a liquid. If I actually go ahead and calculate that delta S using the values from the thermodynamic table of the absolute entropy values, I find that it's negative 79, which is, as I predicted, is a negative value, which means the process will not be spontaneous. But of course, that's just the system. And we know that condensation is spontaneous if we do it below 100 degrees Celsius. So clearly, those two things don't agree with each other. So what we're missing here is that we haven't really calculated the delta S of the surrounding in order to add them up to get the delta S of the universe. So let's turn our discussion then to the concept of delta S of surrounding and kind of understand a little bit how we actually calculate that quantity. So the surrounding in the context of a chemical reaction is sort of like a giant environment. So if my reaction is happening here, the surrounding, and this is my reactants and product, the surrounding is just this giant container that can exchange, remember, heat and matter to that system, to that reaction, right? So again, it could be your, from the closest environment would be your test tube, would be your water that surrounds your reaction, up to the air and everything else around it that surrounds that reaction, okay? So the surrounding is really this huge area right here. And generally speaking, we kind of think of the surrounding as so much larger than the system that pretty much the temperature of the surrounding remains relatively constant. It's just whatever it is. The system's temperature can change up and down, but what happens in the surrounding is the temperature stays relatively constant. This is important because when we calculate entropy change, as you recall, I've shown you this equation a few times. This is an equation that was derived originally from the study of those heat engines, but we can calculate delta S by taking the integral of the heat that's being transferred reversibly over temperature. And if we want to do it for the surrounding, then we just have to do this for the surrounding properties. So the reason I talk about that temperature of the surroundings is because this number here is relatively constant. It doesn't really change this T of the surrounding. It's just because it's so big relative to the system that whatever the system transfers, either absorb or release to the surrounding, doesn't really affect this temperature by a whole lot. However, the top component here is what we need to consider, which is what is the heat that the surrounding either receives or gives away. Well, what happened in the surrounding is not because of the surrounding, it's because of the system. The system is what giving away heat to the surrounding or is absorbing heat from surrounding. And the way that happens is dependent on what kind of reaction is happening in the system. If we have an exothermic reaction, which is the one shown on the right here, our delta H is negative, which means that it's going to release. And where's the heat going to go? Well, it's going to go surrounding. So then that Q value of the surrounding is going to be positive. It's negative with respect to the system, but it's positive with respect to the surrounding. So it's exactly the way this picture is showing. So Q of the system is negative because it's releasing heat, but Q of the surrounding is going to be positive. Okay, and if you have an endothermic reaction, it's the opposite. Q of the system, which is Q of the reaction, is going to be positive because it's absorbing heat. Where's the heat coming from? Well, it's coming from the surrounding. So the Q of the surrounding is going to be negative. It's losing heat to go into the system. Okay, so in other words, there's this opposite relationship, right? System and the surrounding with respect to that heat. And that heat comes from the reaction itself, and it comes from the breaking and the formation of the bonds that happen during a chemical reaction. And so that Q is just your delta H of the system. So it's the delta H that we've been calculating all this time. So in other words, we can make a relationship between delta H of the system with delta S of the surrounding. And specifically, we have an exothermic reaction, it's negative, the delta H. The delta S surrounding will be positive. Whereas if you have an endothermic reaction, the delta H of the system will be positive, the delta S of the surrounding will be negative. Okay, so now we can then combine these things together, again, keeping in mind that temperature doesn't really change for the surrounding. Our equation can then be written as such that delta S surrounding is just the negative of the delta H of the system divided by the temperature of the surrounding, okay? And so that is how we can calculate the value of the delta S of surrounding. To calculate delta H, we can, using any of the methods that you learned in Gen Chem 1, remember that we can use the change in the enthalpy of formation, and to get those thermodynamic values, you can use the same exact table that we use to obtain the values of the entropy. We can also use Hess's law, or we can also use bond enthalpy value, okay? I'm not going to reteach that part of it, but you should review that concept from your Gen Chem 1 note, and then I'll be able to apply problems that require those calculations. So let's take a look real quickly at an example of how now we can combine both the delta S of the system and the delta S of surrounding to calculate our delta S of universe to predict if a reaction is going to be spontaneous or not. So the example here says the formation of ammonia, which is this reaction right here, has a delta S of the system that is negative 197 joules per Kelvin. Now again, before I actually calculate that number, or even if without being given that number, you can tell that this is going to be a negative change in entropy of the system because we have 4 particles of gas going to 2 particles of gas. So it's going to be fewer particles, going to be fewer microstates, right? But we were told that that delta S of the system is negative 197, which again confirms our prediction. We're being asked to calculate delta S of the universe and then to tell us whether the reaction occurs spontaneously or not. Okay, well, we know delta S of the system. In order to calculate delta S of the universe, we're going to need our delta S of the surrounding first. And then afterwards, to tell whether it's spontaneous or not, we need to know whether our delta S of the universe is greater than 0, equal to 0, or less than 0, right? So that's what we need to figure out in this calculation. So I'm going to bring you back to this side here to help us calculate that. I just told you earlier, we learned that delta S surrounding could be calculated using this expression, which is negative of delta H of the system divided by temperature of the surrounding. Now, the reaction is given right here. So what we need to do is calculate the delta H of that reaction. How do I calculate delta H of the reaction? Well, I can go to my thermodynamic tables and then obtain the value of the enthalpy of formation of each of those species and then calculate delta H. Again, this is something that you've done before in Gen Chem 1, so I'm not going to belabor the point here, but I'm just going to show you the actual calculation. We're going to take 2 moles and then multiply it by the enthalpy of formation of NH3 minus 1 mole times the enthalpy of formation of nitrogen plus 3 moles times the enthalpy of formation of hydrogen. Okay, so this is just your products minus reactant with enthalpy of formation. And these numbers I obtained from the thermodynamic table that we were using before to get the absolute molar entropy. So one of the columns listed in that thermodynamic table corresponds to the delta H of formation. So in the end, I get a value of negative 92.22 kilojoules per mole. Always keep in mind that the unit of delta H is in kilojoules. The unit of delta S, the entropy change, is in joules per Kelvin. Okay, so one of the other things I want to point out is, as a reminder, anytime you're dealing with an element in its standard state, like hydrogen gas or nitrogen gas here, their enthalpy of formation is 0. Again, because that's an arbitrary reference state that we define for all elements. Is they're in the standard state, then their enthalpy of formation is equal to 0, okay? All right, so once we have the change in enthalpy, we can calculate our delta S of the surrounding, which is just the negative of the delta H of the system divided by the temperature of the surrounding. We just found that that's the value of the delta H of the system. We put a negative, don't forget that negative in front of it, so it's negative and then negative 92.22 kilojoules over the temperature, which is 298 Kelvin. I convert this to joules per Kelvin just to match the entropy unit that I will need to calculate against later on. So when you convert it to joules per Kelvin, you get 309.5. The delta S of the universe, then it's going to be just the sum of the delta S of the system plus the delta S of the surrounding. And so delta S of the system was given to us as negative 197. Delta S of the surrounding, we just calculated 309.5. Units are the same, so the sum is 112 joules per Kelvin. This is a positive delta S of the universe greater than 0. So that means the reaction is spontaneous at 298 Kelvin. If this temperature is changed and I make this reaction happen maybe at 1000 Kelvin, perhaps that's not going to happen because that number is going to get smaller when the denominator gets bigger. And so that's going to impact the size of this number relative to the negative value. And remember, at some point when the delta S of the universe is negative, then the process is not spontaneous.